Spatial computing functions as a closed-loop biodigital feedback system. It directly links digital processors to human retinas and vestibular canals. The primary engineering challenge here is not maximizing resolution, it is speed. The hardware must translate physical movement into digital light continuously. When visual input lags behind the physical balance data registering in your inner ear, the resulting vestibular-ocular mismatch triggers a biological defense. The brain interprets this sensory conflict as a neurotoxin, causing acute nausea. To prevent this physiological rejection, motion-to-photon latency, the delay between head movement and the corresponding light emission, must remain under 20 milliseconds. A human eye blink takes about 300 milliseconds. The hardware cycle of tracking, calculating, and rendering must complete 15 times faster than that single blink. Reaching this sub-20 millisecond threshold requires a strictly timed pipeline. We are going to trace that path, from the sensors tracking spatial movement to the optics projecting light into the pupil. Achieving immersion requires the hardware to outrace the human nervous system. The process begins with position. Before the headset can draw a virtual object, it must determine the wearer's exact location in physical space. The system tracks 6 degrees of freedom, calculating position along the X, Y, and Z axes, alongside the pitch, yaw, and roll of the skull. The primary tool for this is the Inertial Measurement Unit, or IMU, a cluster of microscopic accelerometers and gyroscopes. On this 3D Cartesian graph, the IMU's high polling rate allows it to detect changes in momentum up to 1,000 times per second, generating a near-instantaneous trace of movement. However, these sensors suffer from integration error. Microscopic miscalculations accumulate over time, causing the generated position to drift away from the true physical location. External optical cameras counter this drift. They provide absolute positional accuracy, pulling the wandering IMU back to reality, though they operate at a much slower 60 Hz. Algorithms like Kalman-Filters perform sensor fusion, merging the high-speed estimates of the IMU with the slow, accurate anchors provided by the cameras. Reliable spatial tracking is the result of this continuous, high-speed loop of error correction. Once the headset knows where the wearer is, it must negotiate the geometry of the surrounding environment. For augmented reality to function, the system has to comprehend the physical geography of the room. Through feature extraction, the software scans camera feeds for high-contrast corners and edges to generate a dense point cloud. SLAM connects these points into a rigid wireframe, mapping the physical room into a 3D coordinate space. This allows the software to establish static anchors, turning a physical table into a measurable digital surface. Render engines use this map to assign fixed coordinates to homograms, preventing them from floating or sliding when the wearer moves. A convincing hologram is locked to an invisible mathematical coordinate that is perfectly aligned with reality. Tracking the room and the head pose only consumes the first fraction of the 20 millisecond latency budget. This timeline represents the sequential pipeline. Tracking computation leads to application logic, then GPU rendering, and finally display scanout. GPU rendering is the most variable bottleneck. Complex 3D geometries cause the render time to fluctuate, often threatening to miss the 20 millisecond deadline. When the GPU fails to deliver a frame in time, the visual stutters mid-pan, instantly inducing severe, immediate disorientation. Engineers use asynchronous time warp as a mandatory software failsafe to hide these delays. Time warp intercepts the pipeline by taking the last successfully rendered image and mathematically shifting its pixels based on the absolute newest tracking data. This distortion happens just microseconds before display, bypassing GPU latency and creating the perception of smooth motion even when the hardware stalls. After surviving the digital pipeline, the frame reaches its final stage, projecting photons onto the human retina. Natural depth perception requires two synchronized actions. The eyes rotate inward to track an object, and the internal lenses bulge to focus on it. When staring at a flat screen 2 inches away, your eyes rotate to look at a distant virtual object, while your biological lenses remain focused on the nearby display. This creates the Vergence accommodation conflict. Resolving this conflict is a matter of physical optics rather than pixel density. Specialized hardware like pancake lenses or waveguides is positioned between the display and the eye to forcefully bend the emitted light. These lenses push the virtual image out to optical infinity, allowing the biological lens to relax and resolve the physical tension. XR displays function as optical prosthetics that override the eye's mechanical focus system. These systems operate concurrently within a single 20-millisecond window. Physical movement registers on the IMU, is corrected by SLAM, and generates a precise geographic matrix. This matrix feeds the GPU, passes through the time warp failsafe, and fires into the optical waveguides. Finally, these bent photons cross the ultimate physical threshold, delivering a perfectly synchronized digital environment directly to the retinal receptors. Immersion is the result of tight integration between tracking math, rendering pipelines, and photonic manipulation. The headset provides the mechanical interface. The human perceptual system performs the actual rendering,